RC circuits have kind of an interesting behavior. They're called RC because they have a resistor and a capacitor. This up here, I think they showed the diagram in the book, but I don't know if I've talked about it yet. This is a switch, so you can close this or open it. And initially, this is open. Okay. Now, if you just have a circuit with capacitors and you close the switch, the capacitor charges up very nearly instantaneously. However, if you put a resistor in here, it actually takes a while for the charge to accumulate on that capacitor because some of those electrons are free to flow through the resistor instead of all just kind of coming and accumulating on the plates on the bottom plate of the capacitor. So what happens is something that charges up over time, and I'm not going to derive this because the derivation requires calculus, but the charge on the capacitor, that doesn't look like a T. This is a T. Charge on the capacitor as a function of time, it winds up charging up at a very predictable rate. We take the capacitance, and this is just the natural number E, not the EMF, 2.71, whatever it is. The capacitance times, oh, I lied. My bad. This is the EMF. Capacitance times the EMF times 1 minus E, the natural number, to the T over tau. And I don't know why they'd like to call this tau, but they do. This tau is just the resistance times the capacitance. And this tau is called the time constant of the circuit. And I don't know why they decided to call it the time constant. It's not like when it's fully charged or anything like that, but it does definitely relate to the temperature, the time, and when various powers of E are involved in the circuit. All right. So if we take this, and you all know calculus, this can tell us something about the current. We know that current is a charge that's passing a point over a time. Well, what this really is that current is the derivative of charge as a function of time. And we have this, so we can say that for an RC circuit, we can say the current as a function of time is, well, C times E times 1 is just a constant, so that's gone. Then we have a derivative of minus E to the T over tau. All right. So we've got a CE that chills out front, a minus that chills out front. We still have an E to the T over tau, and the derivative of this, well, this is E to the T, and this is just a constant, so that's just times 1 over tau. Remember, tau, though, is R times C, so this is then minus C E to the E to the T over tau over R C. And so finally you can see that a factor of C cancels out, and I have made a mistake. This is to the negative T over tau. I apologize for that. That drastically changes how things work. This is negative, which means that when we take that derivative, that negative cancels out. And so our current as a function of time is just the EMF over the resistance times E to the minus T over tau. So these are our two important equations for RC circuits. That the charge is a function of time does this, and the current is a function of time does this. So we can see when T is very small, say it's 0, essentially, we have 1 minus 1 here, which means that the charge at time equals 0 is basically 0, which makes sense. When T gets really, really big, then this is essentially e to the minus infinity, which is 0, and we just have that the charge is capacitance times the EMF, which, makes sense because of our equation that the voltage drop is Q over C. So if we follow what happens with the current, initially at t equals 0, the current is equal to the EMF over R, as though it's only the resistor there. And then over time, as the charge accumulates on the capacitor, current gradually stops flowing. This is an exponential decay. And as time gets really long, the current basically becomes 0 because the charge accumulating on the plates of the capacitor kind of creates its own potential difference that counteracts the potential difference of the battery. That's why charge accumulates on the capacitor in the first place. So we can ask questions about this. Let's say this is a 12-volt battery. Let's say this resistor is 15 ohms, and this capacitor is, I don't know, 12 microfarads. All right. And let's say I want to know, let's find the time constant. Let's find the current at t equals 2 times the time constant, and find the charge, or find the time when the charge is 2/3 of its max. Alright, so tau, that's simple, that's just RC. So our time constant is just 15 times 12 times 10 to the minus 6. That's 1.8 times 10 to the minus 4th. You might, I should have stated that tau has units of seconds. Which makes sense because you can't take e to a power of something that has a unit. So we have to take a time divided by a time. It might seem strange that resistance and capacitance multiplied together get you something in seconds, but if you look at what their SI, what they're made up of, it does work out that way. Yeah, so because resistance, we know V equals IR, and this is, I is just a current, which is a charge over a time, and V is voltage. I'm just going to leave that as voltage. So then R is a voltage times time over a charge. Whereas from our V equals Q over C, a capacitance, you can see, is a charge over a voltage. So if we multiply those together, then look what we've got, just time. All right, so that's 1.8 times 10 to the minus 4th seconds. And find the current at t equals 2 tau. Well, we can do that just by plugging stuff into the formula. Our current is given by this, so we've got 12 over the resistance, which is 15, e to the minus 2, because 2 tau over tau is just 2. So that's 12 over 15 times e to the negative 2, which I guess is why it's called the time constant, is because that's how you get integer powers of e. It's 0.108 amps. So there's still some current flowing when the time constant hits 2, or when we get the time, 2 times the time constant. Find the time when the charge is 2/3 of its max. Well, the max charge is just as though there is no resistor. So that's where the Q over C is equal to the EMF. So the max charge is just the EMF times the capacitance. So that's clearly 144 times 10 to the minus 6th, which would be 1.44 times 10 to the minus 4th. And then we want to find when it's 2/3 of that. So we take 1.44 and we multiply by 2/3. So 2/3 Q max is 9.6 times 10 to the minus 5th. And then we can just plug that into the time formula. We've got 9.6 times 10 to the minus 5th, and we want that to be equal to, up here, the capacitance, which is 12 times 10 to the minus 6th, times the EMF, which is 12 volts, times 1 minus e to the minus t over tau, which was 1.8 times 10 to the minus 4th. So, we've got 9.6 e negative 5. Here, let me, so you can see what my calculator is doing. We divide that by 12 e negative 6 times 12. And then we subtract 1, multiply by negative 1, because there's a negative 1 out front, take the natural log, multiply by 1.8 times 10 to the minus 4th, and then there's also a negative attached to the t, so times negative 1, which is good because we can't have negative time. So the time for the charge is 2/3 of its max, is 1.977, etc., times 10 to the minus 4th seconds. So, I mean, that is still a short amount of time, but it's an appreciable amount of time, amount of time that can be measured. And if you get, if you get larger values for the resistance, it takes even longer. For resistance and capacitance, it takes longer for the circuit to charge up as well. So that's a little bit of how RC circuits work. If you charge up a capacitor, so let's say you've got, it's the same circuit. You close the switch, get the capacitor fully charged, and then you open the switch again. Then basically all that's left is you've got this capacitor and this resistor. And the charge in the capacitor has some charge on both plates, and that's gradually redistributing itself throughout the circuit. So in that case, when you're discharging the capacitor, then the charge as a function of time, it looks a lot like the other equation, but it's equal to that maximum charge times e to the minus t over tau. So it kind of parallels this equation. This c times epsilon is the maximum charge already, and then instead of the 1 minus, we just have that. So that the charge on the capacitor will gradually dissipate, spread itself out over the charge will spread itself back out over the circuit. There are a few things I didn't realize this, but there are a few things that are regulated by RC circuits. Windshield wipers are one of them. How they go back and forth when you change that dial, when you flip that dial, you're adjusting either I think it's the capacitance of something in an RC circuit, and that time constant is how the wipers know when to go back and forth. And sometimes they go really slowly, and sometimes they're like, but that's done by adjusting the time constant of an RC circuit. I didn't realize that. And there are some other things that are on a set time that work that way. The turn signal in a car is also on the basis of an RC circuit. I don't know if you know this, because most of you probably don't drive, but the way cars are manufactured so that turn signals blink faster when the turn signal bulb, the light bulb that operates the turn signal, is about to burn out. So something in the car senses that the bulb is going to burn out soon, and adjusts the time constant of the RC circuit that regulates the turn signal. That's pretty cool. That's a pretty cool bit of engineering. RC circuits are also used in pacemakers. A pacemaker is, well, we have a natural pacemaker that keeps our heart beating in a regular time. But when people have heart issues, sometimes they need a pacemaker because their body isn't properly regulating their heartbeat. And so we have artificial pacemakers, and those two are timed by an adjustable RC circuit. And the last